Hi, everyone. On the half-angle identities, I'd like to show you why identity 17 leads, or how identity 17 leads to identity, say, 18. And then the reasoning is very similar for number 19. I want to show you why these make sense. All right. So over here, it's really kind of a verification problem. In fact, I could frame this as a verification problem on homework, which I've kind of done, and on exams. All right. So tangent of theta over 2. Here's identity number 17 equals plus or minus, where you would have to choose the sign, by the way, of the square root of 1 minus cosine of theta over 1 plus cosine of theta. It's like the sine top over the cosine top. Sin is bad. Sin is negative on top. Minus. All right. So what's our target? Maybe I'll keep the target in mind here. We should keep the target in mind. Our target is going to be 1 minus cosine of theta all over sine of theta. 1 over cosine of theta all over sine of theta. That's going to be our target. All right. Now, here's the deal. We want to get 1 minus cosine of theta all alone on top. Right now he's under a radical. Well, here's a question for you. As long as there are no domain problems, the square root of x times what will give you x? Well, the square root of x times itself will give you x. Meaning that I'm inclined to multiply 1 minus cosine of theta by itself. So I force a square there, and then the radical will basically remove the square. Although there is a subtlety there. Okay, so that's a strategy. Now, some of you might be thinking, well, wait, if I want a 1 minus cosine of theta in the end, why not just square this thing? A lot of students are tempted to do that, but I have a question for you. Is x equivalent to x squared? Is it always true that x equals x squared? No, you can't always say that. In fact, it's usually not true. X is usually not equal to its own square. You don't have the right to square this because you feel like it. However, we can multiply by 1, right? This here is 1. That is legal. You can multiply by 1 in the form 1 minus cosine of theta over 1 minus cosine of theta itself inside the radicand. So on the top, we're getting the square of 1 minus cosine of theta. We're leading to a removal, right? There's kind of almost an inverse deal going on where we can remove the square with the radical on top. And what's happening on the bottom? Well, it's that algebra rule, right? So we have, there's so much purple here. Let's go to blue. Okay, let's go to blue. All right. What is x plus y times x minus y? Whoops. It's equal to x squared minus y squared, if I can type. If you have x plus y and x minus y, their product is x squared minus y squared. All right. So on the bottom, we get the square of 1, which is 1, minus cosine squared theta. And hey, what is 1 minus cosine squared theta? Mr. Pythagoras says it's sine squared of theta. And you can see how we're aiming for that target down there. So by multiplying by 1 minus cosine of theta over itself inside the radicand, we're accomplishing two things. We're setting up for the removal of the radical on top, and we're setting up for a sine deal, S-I-N-E deal, on the bottom because of Mr. Pythagoras. All right. Well, we can basically use an old algebra rule that says that a squared over b squared is the square of a over b. So we can bring the square on the outside. Okay, don't freak out too much about domain right now. So we have the square on the outside by this rule, this algebra rule. And remind me, what's the square of x squared? Well, if x is non-negative, it is x. But in general, it's the absolute value of x, remember? For your A plus, the square root of x squared is technically the absolute value of x. In blah notation, is that. And the absolute value does break up across fractions. Okay, so we have this. Plus or minus the absolute value of 1 minus cosine of theta. That's on the top. All over the absolute value of sine of theta. But wait a minute, I claim that I actually don't need the absolute value on top. Why not? Well, look at the argument inside here. 1 minus cosine of theta. I'll type it out here. We're focusing on 1 minus cosine of theta. But wait a minute, if I have $1 and you take away cosine of theta away from me, at most you're taking away $1 from me, right? That's the highest value in this range, in this guy's range, 1. So 1 minus something that's at most 1, you agree that I'm either left with something or I have exactly 0 left. I don't owe you money, even though you're my thief anyway. But so 1 minus cosine of theta, you agree this is non-negative for all real values of theta. And this kind of thinking comes up a lot in calculus, actually. Now, the absolute value of something that we know is never negative, as a simplification step, we remove the absolute value symbols. We can do that on the top. But wait a minute. Look at sine of theta. Can sine of theta be negative? Oh, you bet it can. It's that sine wave. Does that sine wave go below the horizontal axis? Oh, yes, it does. So sine of theta can be negative. We have no right to remove absolute value down here. We do up here because the argument here is guaranteed non-negative. Okay, so I know that I have this so far, and that's as far as a student can go. It turns out that you don't need absolute value around sine of theta either, but the reason for that is harder to understand. The reason is that tangent of half theta, which was the original left-hand side here, tangent of half theta has the same sign as sine of theta. You could do a quadrant analysis, try some sample angles to see why, but it's kind of hard to explain. You have to kind of play with that. But it turns out you can remove absolute value on the bottom. On an exam, I wouldn't push you on explaining why. But you do get this right-hand side for number 18. That identity way up here. And by a similar reasoning, where instead, since we're going to kind of copy this piece of the radicand down here, if you multiply the radicand here by 1 plus cosine of theta over itself, then you're going to end up with the right-hand side for identity 19. So that's how you get basically these other half-angle identities for tangent, although we did have to take a leap of faith regarding our right to remove absolute value at the end. But the signs, SIG and S, do work out very nicely. There's no ambiguity, like over here for number 17. So those are the half-angle identities. And again, for the product to sum and sum to product identities, there are 4 product to sum identities. These are nice if you're doing derivatives or integrals, because calculus hates squares and also products and quotients. So this is good for calculus. We like to do things term by term in calculus. So going from a product to something that looks more like a sum or a difference. So on an exam, for example, I might give you an expression like this, and I'd have you re-express it. I would show you this block of 4 identities. You pick the right one to use, and then apply it. So basically, on seeing this block of identities, be able to apply the appropriate one. But you wouldn't have to memorize these. Although these can be verified from right to left by using the sum and difference identities. You can plug into here and prove this from right to left. And then from the product to sum identities, you can get the sum to product identities, where you express a sum of sign expressions as a product. This is helpful if you're solving equations, because remember, when you're solving equations, we like having a bunch of factors multiplied together equaling 0, a product of factors equaling 0, and that's good for solving equations. But again, I would say something like re-express something of this form using the sum to product identities. I would give you this list of 4, you pick the appropriate one, and apply it appropriately. So do the homework. So 19 plus 8.